This video is for Physics of the Universe, Unit 1.4, Solving Motion Problems. Today's essential question is, how can position, velocity, acceleration, and graphs be used to describe the motion of an object? Hello, baby birds! We're going to look at how we describe and analyze the movement of objects using three foundational concepts: position, velocity, and acceleration. To make these ideas concrete and a little bit more meaningful, we'll be grounding today's video in the world of dog sled racing. This traditional and fun practice is deeply connected to the Inuit culture and provides us with a perfect real-world context. A dog sled doesn't just move forward at one speed. It starts off slowly, accelerates, reaches a cruising velocity, and slows down or turns when terrain changes. This kind of motion helps us visualize what position, velocity, and acceleration really mean in action. Here's what we'll be learning in this video: position and displacement. We'll explore how we describe where an object is and how far it moves from one place to another. Speed and velocity. We'll look into how quickly an object moves and whether direction plays a role in that. Acceleration. We'll see what happens when an object speeds up, slows down, or changes direction. Graphical representations. Finally, we'll interpret motion by looking at graphs, which let us visualize changes over time. All of these ideas will come together in a narrative like the dog sled race, one that begins at a starting point, accelerates across icy terrain, curves through trails, and finishes with the deceleration at the finish line. So let's start with position. Imagine you're watching this dog sled team on a frozen lake. You need to know where they are at any moment. That location, relative to a fixed point, like the starting line, is their position. Now, let's say the sled begins at 4 meters from the start and moves to 8 meters. That change is what we call displacement. Displacement is a vector, which means it has both magnitude, meaning how far, and direction, meaning which way. We calculate displacement using the formula delta x is equal to x final subtract x initial. In our example just now, our delta x is 8 meters subtract 4 meters, which is equal to 4 meters. So the sled moved 4 meters forward from its starting point. Again, a magnitude, 4 meters, and a direction, forward from its starting point. Now, we need to talk about the difference between displacement and distance. This is a concept that many students get confused about. Let's say the sled races out to a marker, then turns around and returns past its starting point. Now, here's the difference. Displacement only considers the starting and final positions, like drawing a straight arrow from where the sled began to where it ended. It's a vector and can be negative or positive. Distance, on the other hand, is the total ground covered, no matter the direction. It's a scalar, which means it doesn't care about direction, just how much was traveled. So a dog sled that makes a 5-kilometer loop and returns to its starting point has a displacement of 0, but a distance of 5 kilometers. So let's break this down with a more detailed example. So suppose that sled started at 4 meters, moves to 8 meters, and then turns back and ends at 2 meters. The sled didn't go in a straight line. Its path curved and retraced. So we can calculate our displacement. Remember, delta x is equal to x final subtract x initial, which in this case is equal to 2 meters minus 4 meters, which is equal to negative 2 meters. The negative sign here tells us the sled ended up behind where it started. It doesn't mean bad, as in negative. It just tells us direction. Whereas distance traveled, for the first leg, we moved from 4 meters to 8 meters for a total of 4 meters. Then the second leg, we moved from 8 meters to 2 meters, which is a distance of 6 meters. And so our total is 4 meters plus 6 meters is equal to 10 meters. So again, displacement is about where the sled ended up compared to where it started. Distance is about how far the sled actually traveled, regardless of direction. Next, let's compare speed and velocity. So imagine you're tracking a dog sled's motion with GPS. You see it moving at 12 kilometers per hour. That number is the speed, just how fast it's going with no reference to where. Now imagine that GPS also tells you it's going north. Now that's velocity, speed plus a direction. That's why velocity is a vector, while speed is a scalar. So a sled moving in a straight line at a constant speed has constant velocity. A sled turning a corner, even at the same speed, still has a changing velocity because the direction has changed. This is important in racing because even when teams maintain a steady speed, the physics of their velocity changes constantly along winding trails. Now let's go deeper. We have average versus instantaneous velocity. So suppose a sled team travels 6,240 meters north in 4 minutes. First, let's make those units agree and convert minutes into seconds. So we'll multiply that 4 minutes by 60 seconds to give us 240 seconds. Then, the average velocity is equal to 6,240 meters divided by 240 seconds, which is equal to 26 meters per second north. That tells us the sled moved, on average, 26 meters per second north over the entire trip. But at any given instant, maybe starting out slow, then speeding up, or pausing to steer, the sled had a different instantaneous velocity. Scientists, and specifically physicists, use tiny time intervals to zero in on that exact moment-to-moment motion. That is called instantaneous velocity. Acceleration is the rate at which velocity changes. A dog sled might start from rest, pick up speed, and reach top velocity in seconds. That change is called acceleration. The formula for acceleration is A, meaning acceleration, is equal to delta V, meaning the change in velocity, divided by delta T, the change in time. So let's say a sled increases from 12 meters per second to 34 meters per second over the course of 5 seconds. To calculate acceleration, we would take 34 meters per second, subtract 12 meters per second, and then divide by 5 seconds. So that comes out to be a 22 divided by 5, which gives us about 4.4 meters per second squared. So what that means, the sled is gaining 4.4 meters per second in velocity every second. So it's not just about going fast, it's about changing how fast you are going, or which direction you're moving in. In sled racing, that might mean speeding up on flat terrain or adjusting momentum through a tight turn. Here's a more complex race, a race car. Or we can just stick with the sled if you want to. Let's take this race car. No, let's stick with the sled. Let's stick with the sled. It slows down after crossing the finish line. So let's say it drops from 75 meters per second. That number is probably closer to a race car. 75 meters per second all the way down to 23 meters per second over the course of 9 seconds. Acceleration is going to be 23, subtract 75, and then divide by 9, which comes out to be negative 5.8 meters per second squared. That negative sign tells us it's slowing down, what we might call deceleration. Now suppose we want to know how far the sled traveled while slowing down. Well, if it starts at rest, we can use delta x is equal to 1/2 at squared. If the object starts with an initial velocity, meaning v sub I, we're going to use the same equation, but we have to add initial velocity. So it'll be delta x is equal to vit plus 1/2 at squared. These formulas help racers predict stopping distance, which is critical in real-time strategies. Position time graphs help us visualize motion. A flat line means no change in position, meaning, in our case, the sled is resting, maybe pausing on a hill. An upward slope means it's moving forward. A downward slope means it's going backward. A steeper slope means it's going faster. So the slope of the line is the velocity. So if the sled goes from 0 meters to 10 meters in 4 seconds, that's 2.5 meters per second. It's like reading the sled's story. Each part of the graph tells us what it is doing. Velocity time graphs show how velocity changes over time. Here, a flat line above 0 means constant forward motion. A line that slopes up shows acceleration, like the sled powering up in a straightaway. A line that slopes down shows deceleration, maybe braking before a corner. But there's more. The area under the curve tells us the displacement. So let's say that the sled is moving at 2.5 meters per second for 4 seconds. In that case, the area is going to be equal to 2.5 multiplied by 4, which is equal to 10. That is how far the sled traveled in that interval. So let's bring it all together. Position and displacement help us describe where the sled starts and ends. Speed and velocity tell us how fast and in what direction it's moving. Acceleration helps us understand how quickly the motion is changing, meaning speeding up, slowing down, or turning. Graphs help us use visual language to see motion. Slopes are equal to velocity or acceleration, and area is equal to displacement. Every part of a dog sled race, every sprint, turn, and slowdown is a lesson in physics. And now you have the tools to describe it all. At this point, you should be able to generate a full and appropriate response to today's essential question. How can position, velocity, acceleration, and graphs be used to describe the motion of an object?